Hello all, welcome to Learn Easy. We have completed the volumetric relationships in our previous video. So if you didn't, click on the I above to watch it now, or I'll put a link in the description box below. You can watch it after this video. So now moving on to the next term, water content. But before that, I've shown the three-phase system here. For clear observation, I've indicated with the different colors, and this green color may be taken as the voids and the rest is solids. Other observations are pretty self-explanatory. So water content is basically ratio of mass of water to mass of solids. That is, we can do a figure here, comparison of amount of water with respect to solids. Look here, mass of water to mass of solids, the ratio of this part and this part. Basically, it is a comparison of amount of water with respect to solids. Water content is also called moisture content. If the observations are taken from the soil collected from the site or field, water content is represented with the letter W. Therefore, in technical terms, W equals mass of water by mass of solids. Mass of water can also be written as total mass, that is the total soil mass, minus the mass of solids minus the mass of air. But we know mass of air is 0, so we're just not writing it here. So by substituting that, we get water content is total mass minus mass of solids by mass of solids. Now, water content is expressed in percentage, but as in the case of all the previous terms, it is used as a decimal value only in computation. That is, while substituting in any formula. A note here, water content of fine-grained soils are generally greater than water content of coarse-grained soil. So let's take a look into it. Let's just say, for our convenience, I've drawn the fine-grained soils and the coarse-grained soils here. So I've mentioned here that water content of fine-grained soils is generally greater than the water content of coarse-grained soils. As you can see the packing here, as we know, the fine-grained soils have the property called charge. Also, the particle-specific surface area of the fine-grained soil is bigger when compared to that of a coarse-grained soil. Let's just name a few fine-grained soils here: silt, clay, and for the coarse-grained soils, gravel and sand. Let's take clay. We know clay has charge. Its particle specific surface area is more. Some professionals say that the reason behind the water content being more for fine-grained soils than coarse-grained soils is specific surface area being more for fine-grained soils, and also the charge. Some say that the charge attracts water molecules and hence retain more water than compared to the coarse-grained soils. Hence, water content of fine-grained rather than water content of coarse-grained. Now, moving on to the boundary conditions. Water content can be as low as 0 and as high as more than 100%. That means the least value can be 0 and the maximum value can be 100 or more than 100. If the water content is said to be 0 for a soil, that means the numerator, that is the mass of water, should be 0, which means the voids are here. The mass of water should be 0, that is here, which means all the voids, that is the green colored part, are filled with air only. And in that case, the three-phase system becomes the two-phase system, in which all the voids are filled with air only. And this type of soil, we call it as dry soil. On the other hand, if the water content is said to be 100% or more, The mass of water equals mass of solids. In that case, these two parts weigh equally. Let's see how that case looks. So in that case, the three-phase system looks like this. I've represented both these sections with the same color to indicate the mass of the two sections are equal, that is, mass of water equals mass of solids. Now observe, I am representing the voids again with this white color rectangle here, because you should not get confused. These are the voids part and this is the solids part. So now observe carefully, as we have mass of air is 0, even then this particular soil should not be called fully saturated soil. But there is no rule to say that the voids and the solids have to be in equal parts. They may be in equal parts, but that's not necessary. We know mass of air equals 0. But even if mass of water equals mass of solids, it need not necessarily means that the whole voids are filled with water. Because see here, we have air here. The air does not have mass, true, but a part of the voids are filled with air. Since the air is also present, we cannot call the soil as fully saturated soil. I hope you understand the difference. Let's just say in technical terms here, total mass equals mass of voids plus mass of solids. This mass of voids can be written as mass of air plus mass of water. So substituting back into this equation, total mass equals mass of air plus mass of water plus mass of solids. But we know mass of air equals 0. So all that left is mass of water and mass of solids. So total mass equals mass of water plus mass of solids. But as I said earlier, here the blue color representation, air is also present, just the mass is neglected. If mass of water is equal to mass of solids, that never indicates if the total voids are filled with water or air or completely water. So if it is filled with partially air and partially water, such type of soils are called partially saturated soils. Now, you may get confused. You said mass of water equals mass of solids, but this case can occur in fully saturated soils also. Let me show you how. Now observe in this figure. This is the same. Here also mass of water is equal to mass of solids, and here also mass of water is equal to mass of solids. But here the voids have a little air left in them, but here the voids are completely filled with water. But then again, mass of water equals mass of solids. So such type of soils are called fully saturated soils. In this case, we have the water content as 100%, and also in this case, we have the water content as 100%. Because here, all we need is mass of water to be equal to mass of solids. Also, the water content can be greater than 100% in some cases. This happens when water content to be greater than 100%. There are two cases in here also. Let's just take a look at them. Let's this be case 1 and this be case 2. Here, remember, all these representations are of masses only. So this whole represents the mass of water and this whole represents the mass of solids, and the same here. So for case 1, mass of water greater than mass of solids. But the whole voids are filled with water. That means there is no air at all. So this is a fully saturated soil. Whereas in the case 2, there is a little air left in the voids, but here also the mass of water is greater than the mass of solids. As this soil has little air and little water in the voids region, we call it the partially saturated soil. But in both these cases, as the mass of water is greater than mass of solids, we have the water content as greater than 100%. So I hope that explains clearly the range of water content in different types of soils. Also, These two cases indicates that more than 50% of the total mass is water. Another note, water content is an important property. Just with some little variation in water content, the characteristics of fine grained soils can change considerably. That itself indicates the importance of water content in soil mechanics. Water content should be accurate whenever noted. So to wrap it up, least value of water content equals 0, whereas the highest value of water content can be more than 100%. So that is pretty much about the water content, and we'll continue our lectures in the next video. Thanks for watching and make sure to subscribe.